Welcome to this video of Module 4 on Auto Configuration. In this module, we'll be talking about DHCP-v6 or Stateful Auto Configuration. We'll discuss the following topics: how DHCP-v6 works, differences with DHCP-v4 and DHCP-v6 PD. How DHCP-v6 works. DHCP-v6 is the other tool available for auto-configuring network parameters in an IPv6 node. DHCP-v6 is also known as Stateful Auto-Configuration as opposed to Stateless Auto-Configuration. The term stateful refers to the fact that the DHCP-v6 server, which assigns IP addresses, typically stores the state of the assignments, when they are made, for how long, to whom, and so on. DHCP-v6 operation is very similar to that of DHCP-v4. A client sends requests to a server over UDP, and a relay server can be used to forward requests to a centralized server. A few details regarding DHCP-v6. DHCP-v6 messages have different names: solicit, advertise, request, and reply. DHCP-v6 uses UDP port number 546 for clients and port number 547 for servers and relays. DHCP-v6 uses well-known multicast addresses. Clients use FF02:1:2 to send requests to all servers or relays on its link. If it doesn't know their anycast address, a relay server can use FF05:1:3 to find any DHCP-v6 servers within the organization. Finally, stateless DHCP-v6 is only used to auto-configure parameters other than the IP address, for example, the DNS server. It is called stateless because the server doesn't need to store the state of the assignment. It simply receives a request and sends back a response. DHCP-v6 operation is similar to DHCP-v4. The client sends a solicit message, and the server replies with an advertise message offering the requested resource. The client signals what it needs using request, and the server complies using reply. This is what the server would do if it were on the same LAN as the client. Another option is to use a relay server on the same LAN as the client, which would forward the request and replies to a centralized server. This will allow using a centralized server to provide the same service to multiple networks distributed throughout the organization. Here we can see how DHCP-v6 works with a relay server. Differences with DHCP-v4. For those already familiar with DHCP-v4, it is interesting to note the differences between DHCP-v6 and DHCP-v4. A major difference is that DHCP-v6 doesn't provide information on the default gateway, which must be discovered either manually or automatically through router advertisement messages. Another difference is that DHCP-v6 uses DHCP Unique Identifier, or DUID, to identify the client and the server. DHCP-v4 used MAC addresses. DHCP-v6 introduces the possibility of delegating address prefixes, known as DHCP-v6 prefix delegation, a topic we will now discuss in greater detail. DHCP-v6 prefix delegation. In IPv6, there are no private addresses and NAT, which is what IPv4 uses to address and provide connectivity to multiple networks, including those received by a generic router, which automatically configures a public IPv4 address on its WAN interface. A typical example of this is a CPE connected to an ISP. This scenario requires IPv6 addresses for the CPE's internal network. DHCP-v6 PD is a scalable solution that allows automatically configuring these addresses on the routers that need them. DHCP v6 PD operates much like DHCP v6, except that the requested object is a prefix, IA PD. In this example, the CPE sends a request to the DHCP v6 server asking for a prefix. The server replies, as we have seen, and 4 messages are exchanged. The prefix received by the CPE can be subdivided to provide connectivity to more than one internal network. Examples: the most common of the 3 options available for using DHCP v6 is the one where flags M and O are set to 1. That is, the one where DHCP v6 is used to configure the IP address and other parameters. In this scenario, where host A connects to a LAN served by a router, the first thing it will do is generate an interface identifier based on the MAC address and create a link local address by adding prefix FE80 to this locally generated interface ID. It will then check that the address is unique, and if everything is okay, it will configure the interface. Next, it will send a router solicitation to the well-known all routers multicast address. Our router will be listening on that multicast address and will reply with a router advertisement in this case, with flags M and O set to 1, which tells the host that it must use DHCP v6 to configure both the IP address and the DNS server. The host will begin the DHCP v6 message exchange. The first message will be a solicit message sent to the multicast address of all DHCP v6 relay servers. The router, which in this case is acting as a relay, will forward the messages to a DHCP v6 server and receive replies, which it will also forward to the host. The message exchange is completed: solicit, advertise, request, and reply. Once the host receives the last message, it will have all the information needed to configure its network parameters, an IP address, and 1 or more DNS servers. The next step is for the host to configure the default gateway, notation :/0, pointing to the router's link local address, learned through the router advertisement it received initially. Now, the router has all the parameters it needs to communicate on the network. There are 2 other auto-configuration options where DHCP v6 may be used. When flag O is 1 and flag M is 0, DHCP v6 will be used to configure other parameters, and SLAC will be used to configure the IP address, just as we saw in the video on stateless auto-configuration. The host will then initiate the DHCP v6 exchange, just as in the previous example, except that in this case, the only information it would obtain is the DNS server. The other option is when flag M is 1 and DHCP v6 is only used to configure the IP address. In practice, this option is not used, as SLAC will be needed to configure the DNS, and operating systems do not currently offer this possibility. Thank you for your attention. We have just watched this video on DHCP v6 or stateful auto-configuration. In the next video, we'll be talking about some conclusions.